In this section we learn about patterns in detail. Pattern expressions consist of observers, operators and guards. Observers are the basic building blocks. Observers are atomic expressions, they are the simplest type of expression. Observers react to events arriving or time passing. To react to an event arriving, name the event type and add any filter expressions. The withdrawal amount greater 200 reacts when a withdrawal event with an amount greater than 200 comes in. To react to time advancing, there is the timer interval and other timer syntax. The timer interval 10 seconds reacts to 10 seconds passing. Patterns connect observers with logical operators. The logical operators are and, or, and not. Patterns have operators that control repetition. The operators that control repetition are every distinct, brackets num, and until. Patterns often use a temporal operator that defines an order of observation. The syntax for the temporal operator looks like an arrow, and is the characters dash and greater. Guards control when an expression ends, so they control whether an expression stays alive or should terminate. Patterns combine observers with operators and guards. The pattern below is a pattern that matches when either a withdrawal event with amount greater than 200 comes in or when a time interval of 10 seconds passes. It reads, withdrawal amount greater than 200, or timer interval 10 seconds. This slide is about how observers, operators and guards interact. The slide also explains the dynamics of pattern state. To give you some background, patterns are based on the repeat event pattern language of Stanford University in 1996. The compiler parses a pattern into an expression tree according to operator precedence rules. The operator precedence rules are pretty intuitive and can be found in the documentation. When the pattern starts, the runtime starts the topmost expression. Each expression decides which sub-expressions, if any, to start. And so on down the expression tree. Thus, starting a pattern, only the relevant sub-expressions start, and not all sub-expressions need to start. Arriving events or advancing time trigger observers. Observers indicate the change to their parent expression. Parent expressions handle the change in truth value by starting and or terminating sub-expressions, indicating the change to their parent expression or causing the pattern to fire. The overall pattern state is a tree of activated expressions. Let's talk about tags. Tags are a name that you can assign to a matching event. Tags are optional. It is not necessary to assign a tag to an event. The syntax starts with the tag name. After the tag name is the equals character. After that is the event type name and the optional filter expressions. The tag is an optional name for a matching event. The tag name can then be used by other pattern expressions and in EPL clauses such as the select clause. Suppose that the pattern matches a withdrawal or a deposit event. This EPL assigns the tag W to the withdrawal event and the tag D to the deposit event. In the select clause, it selects W.amount and assigns withdrawal amount as a column name, and it selects D.amount and assigns deposit amount as the column name. When not assigning a tag to events, the runtime does not keep untagged events in pattern state. Also, the runtime does not output untagged events. To show you what I mean, the below EPL has no tags. The result are, when the pattern fires, output rows that have no columns. The followed by operator is often used when an event or a time interval follows another event or time interval. The followed by operator looks like an arrow. It consists of a dash character and a greater character. Let's say we want to detect a withdrawal event followed by a matching deposit event. The account ID of the deposit event must be the same as the account ID of the withdrawal event. The EPL is: select star from pattern W equals withdrawal followed by D equals deposit parenthesis account ID equals W dot account ID. For this pattern to fire, the order of observation must match. The withdrawal event must arrive before the deposit event. When the pattern starts, the runtime starts looking for withdrawal events. The runtime does not yet look for any deposit events. This is because the followed by operator only starts the first sub-expression with is looking for a withdrawal event. When we say that the runtime does not look for any deposit events, it means that deposit events are ignored and there is no state associated to tracking deposit events. When a withdrawal event arrives, the runtime stops looking for withdrawal events. The runtime then starts looking for a deposit event with a matching withdrawal event account ID by comparing W.account ID. The W is the tag name assigned to the withdrawal event. When a deposit event arrives, the runtime stops looking for deposit events and the pattern is done. This pattern does not have repetition. When the pattern is done, the runtime no longer looks for any withdrawal and deposit event, and there is no state associated to the pattern or to tracking withdrawal or deposit events. Use the AND operator to connect observations that can occur in any order. Suppose that we need to detect a withdrawal event and a deposit event, in any order. The sample is simply: select star from pattern W equals withdrawal and D equals deposit. Here, the observations can be in any order. The deposit event can arrive before the withdrawal event or the withdrawal event can arrive before the deposit event. No correlation criteria can be placed in filter expressions, since the observation is in any order. When the pattern starts, the runtime starts looking for withdrawal as well as deposit events. Let's assume, for example, a withdrawal event arrives. The runtime stops looking for withdrawal events and then remains looking for deposit events. Let's assume, for example, a deposit event arrives. The runtime stops looking for deposit events, the pattern fires and is done. The output row has two columns, the W column contains the withdrawal event and the D column contains the deposit event. Use the OR operator to connect observations wherein one observation only needs to occur. Suppose that we need to detect a withdrawal event or a deposit event. The sample is simply: select star from pattern W equals withdrawal or D equals deposit. The first observation triggers the OR operator. When the pattern starts, the runtime starts looking for withdrawal as well as deposit events. Let's assume, for example, a withdrawal event arrives. The runtime stops looking for withdrawal events and also stops looking for deposit events. The pattern fire and is done. The output row has two columns, the W column contains the withdrawal event and the D column contains a null value. For this example, either the W column or D column in the output will be null depending on whether a withdrawal event arrived, or a deposit event arrived. This page is about nesting expressions by using parentheses. The remainder of the slides don't have select star from pattern, so the slide text can be shorter. Note, the EPL syntax does require select star from pattern. Imagine that we want to detect a withdrawal event followed by a PIN change event and a password change event with a matching account ID, wherein the PIN change and password change events must always come in after the withdrawal event but can come in any order. The text is W equals withdrawal followed by parenthesis. PIN equals PIN change and PWD equals password change. Take notice of the parenthesis after the followed by operator. The parentheses surround the expressions connected by the AND operator, which is pin equals pin change and pwd equals password change. The parentheses ensure that, after a withdrawal event comes in, the pattern looks for both pin change and password change in any order. For instance, assume the following scenario. A scenario is a specific sequence of events arriving in time passing. Upon pattern start, the runtime only looks for withdrawal events and does not yet look for pin change and password change events. A withdrawal event arrives, and the runtime stops looking for withdrawal events and starts looking for pin change and password change events with matching account ID. A pin change event with a matching account ID arrives, the runtime stops looking for pin change events and remains looking for password change events. A password change event with a matching account ID arrives, the runtime stops looking for password change events. The pattern fires, is done, and the output row has 3 columns W, pin and PWD. The next 2 slides are about controlling repetition with the every keyword. The examples we have seen earlier all complete after one pattern match. Patterns can get restarted, for instance, when using contexts, discuss later. The every keyword can be used for repeat observation. Thus, output every withdrawal event followed by a deposit event with the same account as the withdrawal event. The pattern is every W equals withdrawal followed by deposit parenthesis account ID equals W dot account ID. The scenario to illustrate is: upon pattern start, the runtime starts looking for withdrawal events. When a withdrawal with account A comes in, the runtime starts looking for a deposit with account A. Now the runtime is looking for withdrawal events and for a deposit with account A. This slide continues the scenario of the last slide. When a withdrawal with account B comes in, the runtime starts looking for a deposit with account B. Now the runtime is looking for withdrawal events and for a deposit with account A and for deposit with account B. When a deposit with account for A comes in, the runtime stops looking for a deposit with account A and the pattern fires. Now the runtime is looking for withdrawal events and for a deposit with account B. When a deposit with account for B comes in, the runtime stops looking for a deposit with account B and the pattern fires. Now the runtime is only looking for withdrawal events and is no longer looking for any deposit events. As you can see, the runtime adds and removes interest in deposit events individually. This can mean more overhead as compared to using a join. Also, when no matching deposit event comes in, it will look forever for this event. For controlling repetition in respect to distinct values, there is the every distinct keyword. Suppose we look for login events followed by a logout event for the same user, ignoring login events for the same user for 10 seconds. Every distinct a.user, 10 seconds a equals login event followed by b equals logout event user equals a.user. This works just like every, but it remembers values for a certain time period and suppresses duplicates. The syntax has a list of one or more criteria expressions that return the value or values, and a time period. You can make use of timer interval when there is a time interval that must pass. The timer interval syntax takes a time period expression. The timer interval expression becomes true after the given time interval. Say we want to fire after 10 seconds. The pattern is simply timer interval parenthesis 10 seconds. When the pattern starts, the runtime adds a schedule to its scheduling, causing a callback when 10 seconds pass. When 10 seconds of time advance, the pattern fires and the runtime is no longer tracking a schedule. The not operator negates the truth value. The not operator negates and flips from false to true and from true to false. An expression with a not operator is considered true at the start. When the expression within not becomes true, the not expression itself becomes false. The case we are presenting here is to find login events followed by a 20-second interval without a logout event arriving within the 20 seconds interval after the login event. The patterns is every login equals login event followed by parenthesis timer interval 20 seconds and not logout event user equals login user. Later slides have a detailed sample scenario. When a sub-expression of and becomes false, the whole and expression becomes false and terminates. Not is usually used with timer interval or some other kind of timer. The timer at works like the cron tab utility of the Linux operating system, and becomes true at the given time and date. The syntax can specify minutes, hours, days of month, months, days of week and, optionally, seconds, time zone, milliseconds and microseconds. For example, a pattern that fires every 15 minutes between 8 a.m. and 5 p.m. on even days is shown next. The EPL is every timer at parenthesis star divided by 15,8:17, square brackets star divided by 2,1, star. Upon pattern start, the runtime computes the next time the cron tab must activate based on the current time, and adds a schedule to its scheduling, causing a callback when time advances past the computed time. Upon time advancing past the computed time, the pattern fires, and since this example has an every, the runtime computes and adds a new schedule. Guards control the lifecycle of the preceding sub-expression. The guard timer within ends the sub-expression after a given interval. Let's say we want every login followed by a logout, same user, within 2 seconds. The pattern is every login event followed by logout event with matching user where timer within 2 seconds. The guard timer within x ends the sub-expression after a given interval or when a count is reached. This EPL returns up to 10 events for 5 seconds. Parenthesis every login event where timer within max 5 seconds 10 events. The guard while ends the sub-expression when the expression is false, and allows it to match repeatedly while it returns true. Here it looks for login followed by multiple page hits until it hits a specific URL. Every login event followed by page hit event for the same user while page hit URL not equals ABC. The repetition operator brackets num defines a target number of repetitions. This example pattern outputs pairs of 2 login events. The pattern is every brackets to login event. The repetition operator brackets low-high sets lower and upper boundaries and can provide an until expression. Output every login event followed by 1 or more login events for the same user, collecting those, performing output at the time when a logout event arrives for the same user. The pattern is every login event followed by parenthesis brackets 1. Login event until logout event. Any given arriving event participates in all available matches among all currently active sub-expressions. To illustrate, consider the following example. W1 equals withdrawal with an account of A or B. And W2 equals withdrawal with an account of B or C. As you can see, A withdrawal event for account B matches both sides of the AND. Consider the following scenario. Upon pattern start, the runtime starts looking for a W1 withdrawal event which has account A or B, and the runtime also starts looking for a W2 withdrawal event which has account B or C. Assume a withdrawal event with account B comes in. The event matches both sides of the AND expression. In the output row, columns W1 and W2 are the same event. EPL can suppress duplicate pattern matches using the annotation suppress overlapping matches. The @ sign is for annotations. The suppress overlapping matches annotation makes any given event in a pattern participate in just one match and not in further additional or later matches. The runtime evaluates this at the time the pattern fires and, at that time, ends sub-expressions that keep the same events as found in the current match. Events must be tagged for this to work. Such as, in this EPL, which returns pairs but never outputs the same event twice. Select A1.id, A2.id. From pattern at suppress overlapping matches brackets every A1 equals A followed by A2 equals A parenthesis A1.id equals A2.id. In EPL, a pattern can be used in many places. The from clause can have one or more patterns, but not in subqueries. The on action clause is for use with named windows and tables, discuss later. Patterns can also appear in contexts, discuss later. This example EPL is a join that uses a pattern to add a delay. It returns, among the last 10-page hit event, those events that match the user. It outputs such matches only after 1 minute passed after each distinct login event per user. Select star from pattern every distinct user 1 minute login event. Followed by timer interval of 1 minute. Unidirectional. Page hit event at length 10 is PHE. Where it.user equals PHE.user. Remember, the as keyword assigns an event name. Remember, the unidirectional means output only when the pattern fires. The next 4 slides discuss a sample pattern that has a timer interval, as well as a not operator. This sample finds login events followed by 1 minute without a matching logout event. The pattern is every a equals login event followed by parenthesis timer interval 1 minute and not b equals logout event user equals a dot user. A concrete scenario follows that spans the next 3 slides. The scenario starts at time t0, the time of that the EPL gets deployed and the pattern starts. After the pattern starts, the runtime has one active sub-expression. Every login event. Now the runtime is only looking for a login event. Assume that at time t1 a login event LE1 arrives for user equals 10. After processing this event, the runtime has 2 sub-expressions active. The sub-expression every login event. The sub-expression timer interval t1 plus 1 minute and not logout event for user 10. Now the runtime is looking for more login events, it is tracking a 1 minute time interval, and it is also looking for a logout event for user 10. This slide continues the scenario started in a previous slide. Assume that at time t2 a login event LE2 arrives for user equals 20. After processing this event, the runtime has 3 sub-expressions active. The sub-expression every login event. The sub-expression timer interval t1 plus 1 minute and not logout event for user 10. The sub-expression timer interval t2 plus 1 minute and not logout event for user 20. Now the runtime is looking for more login events. It is tracking two 1-minute time intervals, and it is also looking for a logout event for user 10 and A for a logout event for user 20. This slide continues the scenario started in a previous slide. Assume that at time t3, time advances, and t1 plus 1 minute passes and logout event not received. The runtime removes sub-expression timer interval t1 plus 1 minute, and not logout event for user 10, and the pattern fires and produces output. The runtime has now only two sub-expressions active. The sub-expression every login event. The sub-expression timer interval t2 plus 1 minute and not logout event for user 20. Now the runtime is looking for more login events. It is tracking one 1-minute time interval, and it is also looking for a logout event for user 20. This slide continues the scenario started in a previous slide. Assume that at time t4, a logout event for user 20 arrives. The runtime removes the sub-expression timer interval t2 plus 1 minute, and not logout event for user 20. The runtime has now only one sub-expression active. The sub-expression every login event. Now the runtime is only looking for more login events and is no longer tracking any time interval and is no longer looking for logout events. The pattern does not fire since the not operator becomes false when the logout event arrives,